Hello everybody, my name is Delphine Dobler and I work for the Institute of Research for Development in the LOBS Laboratory of Physical and Spatial Oceanography. I work with Dr. Christophe Maes and Dr. Elodie Martinez. Today I'm presenting you our work, Mapping the Connectivity of the Major Rivers in Indonesia, a Lagrangian Point of View. This work has been funded by the French Agency for Development. The study aims at understanding the spatial and time patterns of belching of marine debris coming from Indonesian river sources. We use a numerical experiment and a probabilistic approach. We have two main objectives. First, we want to identify the accumulation and dispersion in the open ocean. And second, we want to identify the beaching location of marine debris and the connection with the river sources. For that, we used our ion software of Lagrangian advection to advect particles with a merged surface currents product distributed by the Copernicus Marine Service. This product includes three types of surface currents: outputs from an ocean global circulation model from Mercator Océan, tides from FES 2014, and surface torque strip from a Météo France wave model. With these currents, we advected 2 million of numerical particles during 4 years of simulation. And first, we need to position these particles in space and time. We selected 21 river mouths to position our particles based upon 3 criteria. First one is an identified polluted river, either by the KKP, the Ministry for Maritime Affairs and Fisheries, or by the Ocean Cleanup Project. The second criterion is based upon high population density, either at the mouth or upstream the river, using the NASA SEDAC dataset. And finally, the third criterion is based upon river discharge, using the Copernicus Flood Awareness dataset. As you can see, 9 of the 21 rivers are unsurprisingly located in Java, and the rest of them is distributed in Sumatra, Kalimantan, Sulawesi, Maluku, and Papua. Now that we have set up where to release our numerical particles, we also need to set up when to release them. And for that, we chose to follow the temporal evolution of river discharge. And now, the last thing to do is to define what is considered as a beaching in our numerical experiment. This is done as follows. We define a threshold distance to the coast below which the numerical particle is considered as beached. The coast is represented here by the numerical coast to stay consistent with the used surface currents, and the threshold is smaller than the grid cell size, as many narrow straits in the Indonesian region are only represented by 1 or 2 grid cells. On the scheme, you can see an example of the Sunda Strait representation in the numerical model grid. Now that we have set up the configuration, we can compute the trajectories of the numerical particles. Based upon them, we computed the average number of particles in each grid cell for the last year of simulation. Out of the 2 million of released particles, 10% are still at sea inside the regional domain at the end of the simulation. 30% have exited the domain, mainly through the Indian Ocean. And out of these 2 million of particles, 60% have beached during the experiment. Now I'm going to talk more thoroughly about the space and time distribution of these 60%. First, let's have a look at the time distribution. What is clearly observed is a seasonal signal with 2 seasonal peaks, one centered around January and February, and one centered around June and July. We also have another piece of information here, namely that all river sources contribute to the beachings, from 1.9% for Daly River to 6.5% for Humber River. Some of the rivers with the highest contribution to beachings have river mouths located in enclosed marine zones, such as Ambon or Surabaya, which could have been expected. Now let's have a look at the spatial distribution. The highest values are mainly close to river mouths. 92% of the beachings from Indonesian river sources mainly occurred on Indonesian coast. We computed the corresponding distance from river source to the beaching location for each particle, and 76% of beachings occurred within 1,000 km of the river source. To this general behavior in terms of space and time distribution, we also note some disparities depending on the subzone considered. For instance, if we look at North Java, the beachings come mainly from 6 local river mouths, all located on its coast, and the seasonality follows the regional one. But if we look at West Sumatra, the beachings come also from remote sources, namely Talo River on Sulawesi coast, and the temporal distribution shows only one peak, broader and centered around December. Here are the preliminary conclusions of our study. Beachings occur mainly close to the river source in time and space, have a marked seasonality linked to the monsoon signal, and finally show variations to this global behavior depending on the subzones of beachings. But there remains open questions and perspectives, as for instance the grid resolution impact. As you saw, straits are poorly resolved and so are coastal dynamics. For that, we have a final resolution modelization ongoing. Our second open question is the impact of the interactions between physical processes, because here we simply added all three components to each other. For that, we have a tight coupled modelization ongoing. And finally, we concentrated on the regional behavior, but we have to understand what is the fate of the 30% of particles that exited our regional domain. So these are the perspectives for our work in the future. I thank you very much for your attention.